Now that we've parsed our program text into an abstract syntax tree, we need to evaluate that abstract syntax tree. For an arithmetic expression, evaluation means to turn the tree into a value. If we were dealing with some other language, we might be evaluating it for side effects rather than just for a value. Or in the case of most real-world programming languages, we're evaluating it for both side effects and a value. So the way we specify formally the method to evaluate an abstract syntax tree is called operational semantics. And operational semantics is a series of rules that describes how pieces of a tree can be evaluated, and then we can apply those rules recursively to evaluate the entire tree. Operational semantics are made up of rules called judgments, which look like this. They come in three basic parts. Above the line, we have the preconditions that must be met before this rule can be applied. Below the line, we have two parts. On the left of the arrow, we have a pattern that describes the sort of thing that this rule applies to. And then, if we can match that pattern and we've met the preconditions, then we can transform the pattern on the left of the arrow into the result shown on the right of the arrow. Let me show you the simplest case. If we have a number, then the number is shown by the expression e in this judgment. And we have to meet the precondition that e is in fact a number. And once we've met that precondition, we can evaluate the expression e into the value of the number. So if the expression is 1, then it meets the precondition, and it can be evaluated to the value 1. A more complicated example is addition. The expression e sub 1 plus e sub 2 is what an addition expression is always going to look like. We have an expression on the left and an expression on the right, and an addition symbol in the middle. In order to apply this rule, we first have to meet the preconditions. We have to have evaluated the expression on the left into a number, and we have to have evaluated the expression on the right into a number before we can actually apply the rule to evaluate this addition. But once we've met that precondition, and we have the two numbers for the left and right sides of the addition expression, we can generate the value of this expression just by adding them together. And the rules for subtraction, multiplication, and division look the same. You put in the right symbols instead of addition. You should be able to figure out negation yourself. There'll probably only be one expression rather than two of them. And so once we have this full set of rules, which I showed you the patterns for all of them at this point for the arithmetic expressions that we're going to be dealing with for the first exercise, we can apply the rules recursively. We start at the root of the tree, and the problem when we're at the root of the tree is going to be that the preconditions for the root of the tree won't have been met unless it's just a number itself. And so we're going to have to evaluate both of its children before we can evaluate the root. And once we've recursively evaluated all of the children of all of the nodes, gotten to the leaves necessarily have to have values. They're going to be numbers. We'll be able to recursively go back up the tree and find the value of the root. Let me show you an example for this problem. So let's say we have an expression. 1 plus 2 times 3, right? So that's going to be the abstract syntax tree plus 1 times 2, 3. So we start at the root. And the judgment rule for addition is we need to have evaluated the left-hand side and the right-hand side. Before we can actually add together the values. So that means we need to recurse. And so the judgment rule for multiplication is exactly the same as for addition, except we do multiplications. And it actually doesn't matter which order we traverse the tree in. I guess it might make more sense to reverse the left side down first. So we can see that the value of e sub 1 for addition is going to be 1. And we can see that the value for e sub 2 for the addition we can't figure out until we do the multiplication. So we come down and look at the left-hand side of the multiplication, because we need to do its children first. And so we can go ahead and figure out that the value of this 2 is going to be 2, the value of the 3 is going to be 3. We can then multiply the 2 and the 3 to get the value of the multiplication, which is 6. And now that we have both of the children of the addition, we can do the addition and find out that the value of the expression is 7. So hopefully that made sense. We're going to go ahead and implement these things in Haskell, where it's a little bit clearer than my terrible handwriting.